Alrighty, Dr. Trent, sorry.
Nice.
Thank you.
Yep.
I think I might legit be here till like 11 tonight.
Okay.
That's literally what I told him I want.
Well, you guys will both be here, so at least you won't be here by yourself.
That's true. I wonder if we're gonna have a packed house for today's class too. I always thought that was so weird. Like you have the option for in-person class, and you got like, because I used to have in biomechanics all the time. It would be like the same 2 or 3 people. And I'm like, if I'm trying to come to school, I don't want to just like sit down at home all day.
You're paying all this money for a master's degree. I was like, why would you want it?
Well, to be fair, biomechanics had a lot of undergrads in it.
Mhm.
Okay, that's fair, I guess. I don't know. I still pay attention. I refuse to buy the parking permit because I'm here 2 days out of the week on weekdays, and then I have a Saturday class, which they don't charge you to be here on the weekends. So I know we had like 2 or 3 weeks that we did virtual to start off the semester, and I was like, it's literally cheaper for me to pay $10 a day coming here.
They gouge you for parking here.
Yeah.
It's insane. Hey, how's it going?
If I crank it up a little bit.
What? The heat? Oh, yeah. Just how much are you gonna do?
Like 3 degrees.
What is it right now?
Are you hot?
I mean, I'm comfortable.
I'll leave it. I can wait another hour and 15 minutes.
All right, all right.
Dr. Train, do you have any idea what you're gonna teach next semester?
I have no idea.
No idea.
I am going to take a reduced teaching load though, because I'm taking over some of the academic advising.
Okay,
And so that means I'll teach only 3 instead of 4 courses.
okay.
The only one I know for sure is I'm going to teach the undergraduate finite element course,
All right.
410. Just because no one else teaches that one. And so, but besides that, I'm not sure. All right, it's 7 o'clock, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Good, good. All right. So today we have just a little bit left over from last Wednesday we want to finish, and so I think we just had the assembly part of the code. So what I did was I already posted the solutions from the activity from last week, and so what we'll do is we'll just go very quickly over the assembly. You know, it should be very straightforward compared to the trust code. And then we're going to go ahead and launch into the next set of lecture notes, which is on 2D finite elements. Okay. And so we're going to be focusing on 2D general finite elements for basically the rest of the class. You know, there's a lot to go over for it. And so today we're kind of just setting the, you know, you can think of it as kind of setting the stage. So, you know, compared to 1D finite elements where, you know, we could do a lot of 1D finite elements with, you know, pretty elementary calculus that you would probably see in Calc 1, Calc 2. In 2D finite elements, we need some more advanced integral theorems, some more advanced calculus, multi-dimensional calculus, multivariable calc. And so, I know, at least for me, I always forget the stuff when I don't use it. And so we're going to spend our day kind of reviewing a lot of that stuff, and we're going to describe how it's related to finite elements. All right, so before we start, I do have one announcement. And so on Wednesday, I will not be here on campus. I have a doctor's appointment on Wednesday. My back is kind of giving me a lot more issues, and so I'm going to go see a doctor. But because I teach another class before this, I don't think I can make it back to campus in time to teach the class. And so I'm just going to take a work from home day. And so the lecture on Wednesday will just be virtual only. And so if you're already attending virtually, you can just do the same things as you have been doing. But if you do come here, we are blessed to be in a computer lab, and so you can just use the computers here to view the lecture. Although I don't know how the audio works here for that. Or you can just view it on your laptop, whichever is more convenient. And I'll send an email out tomorrow just to remind everyone about that. Okay. And so today you might see me kind of like stop to like stretch a little bit just because my back's really been bothering me. But yeah, hopefully Wednesday the doctor will give me some good advice. Okay, and so that's it for the announcements. And so are there any questions I can answer before we get started? Okay, all right, so let's go ahead and let's go back to last Wednesday, right? And so last Wednesday, I'll go ahead and share my screen. Okay, last Wednesday, we were looking at this presentation right here, right? And so we were learning how to implement the 1D boundary value problem in Matlab, right? So we spent the majority of the day, I guess last time we talked about the final project as well, and so we talked about how to implement these things. Okay. And I think we stopped about right here. And so we stopped at the point where, we filled in the element stiffness matrix and the element forcing vector, right? And so for the element forcing vector, we applied our Gauss quadrature to evaluate the integral, okay? As well as we evaluated the Neumann boundary condition on the right, okay? And so now we're at a point in the code where we have all of our element stiffness matrices and all of our element forcing vectors, they've all been assembled. And so the next thing to do is just to assemble them into the global matrix. Okay. And so we've done assembly, dozens of times before. This is no different. And in fact, you could think of it as even easier. Okay. And so if we go back to our domain, our domain looks something like this. And so we have basically a 1D domain, and all the elements are listed kind of sequentially. And so think back to when we first started this class. So when we first were doing like a 1D spring problem or a 1D truss, right? All of our elements look like this. Okay? And when we assembled this into the global system, right? Our element stiffness matrix looks something like this. So here's our matrix. And when we inserted, let's say element 1 right here, right? Element 1's contributions would go something like this. Elements 2 contributions would look like this, and so you'd have an overlap just on the top square. Okay. Element 3 is just like that. Element 4 is just like that. And of course, I poorly planned this matrix, but you get the idea, right? And so for 1D general finite elements, we follow the exact same structure. And so the key for this is that when we're on element I, right, where I being one of the element IDs, then our node 1 is going to be, is going to have the same index as that element I, and node 2 will be I plus 1. Okay. And so let's see how that's implemented in the code. And so, if we go, I posted let me go away. Okay. And so if you go to our week 12 page, you can see I've already posted the solution. And so you can see kind of the full solution. Okay. And here is the part with the assembly. And so you can see here we have 4 lines, right? Because our element stiffness matrix in this case is 2 by 2. Right. And so for a 2 by 2 element stiffness matrix means we have 4 entries to include, right? And we basically add these entries in one by one. And so we start with the 1, 1 entry of the element stiffness matrix, then we do the 2, 1 entry, then the 1, 2 entry, and then the 2, 2 entry, right? And so, just like we did with the truss code, we have this update notation, where we said that the global stiffness matrix at this location is equal to the same location, right? And so we don't want to overwrite that, plus the new contribution here. Okay. And so you can see here the pattern of IEs match 1s and 2s, right? And so whenever you have a 1 here, that means we're going to insert that at location IE, where IE here is the loop index, because remember, we have to loop over every single element stiffness matrix, right? And so whenever we have IE, that means we're going to go 1, 1, IE plus 1 is 2, and so on and so forth. And so you need to make sure you do this for every single element stiffness matrix, okay? Of course, what's a little bit different here is that we're adding our global, our element forcing vectors as well. Okay? And so this adds contributions to the global forcing vector. Okay. And so before, if you think back to when we did our direct stiffness problems with trusses and frames and beams, right? The only entries that went into our global forcing vector were due to our modes, right? Were due to our Neumann boundary conditions. Here we have the exact same thing, right? And so we're going to be adding those contributions. It's just that we kind of added them up above instead of down here, right? And so these element forcing vector contributions, they're going to have the modes associated with them. But what's new here is that we're also going to add a body force in as well. Okay. So this is Neumann mode BC and body force / thermal generation. And so, that's kind of what we did at the end of class last time. We use our Gauss quadrature, to evaluate those terms. So we evaluated the contributions from the body force. Actually, in this case, I think it was the thermal generation, as well as the Neumann boundary condition. Okay, and so we have a similar structure here to add those contributions to the global forcing vector. Okay. And so from there, we have to also apply our Derisive boundary condition. And so I believe we went over this last time. And so, when we apply the Derisive boundary condition, first thing we do is we zero out the corresponding row. Okay. And so in this case, since we have a Derisive boundary condition on the left side of the domain, that means we're going to zero out the first row. Okay. And so that's why we have a 1 right here. Then after we zero out the first row, we're going to put a 1 on the diagonal of that row. Okay. And this last line is new. And so before, remember when we have a Derisive boundary condition for structure mechanics, usually that Derisive boundary condition is 0 because we add a fixed point. But for a thermal case, we're instead specifying it to be the specified temperature at that location. Okay. Okay, and so now that we've added all the element stiffness matrices, we have applied our boundary conditions, and so the next step is to solve, right? And so this code is good to go, and so you can go ahead and run it. And I think in this first case, I ran it with 50 elements, right? So let's see what the solution looks like with 50 elements. Okay, and so you can see here that the two solutions are basically on top of each other, and so you can't even tell that there are two on there, because they are almost exactly the same, right? And so let me go ahead and lower this a bit. So let me go ahead and lower this to, let's run it with 5 elements, okay? And so based on what we know with finite elements, if we only have 5 elements here, it's going to be a lot more inaccurate, okay? And even with 5 elements, it still does a pretty good job of estimating, right? So the only difference, let me go ahead and maximize this. I guess you see it a bit more when you maximize, right? The only place where you kind of really see a difference is kind of on this right side right here, okay? It's a little bit hard to tell, but if you kind of notice from the blue, and actually let me turn off the red here just so you can see a bit better. Okay. All right, so let me turn this off. Okay, it's still kind of hard to tell. But if you notice how this solution is broken down, right? What you can see here is that if you look in between this location right here, right, you'll see that there's kind of a little kink in the solution there, and this part of the solution right here, right? If you look at the solution in between these two nodes, then you'll see that the solution is linear, right? And so it should just be a straight line. remember when we derived our element stiffness matrix for this problem, we assumed that our shape functions were linear, right? And so for a linear element, what you have here is a linear variation of the solution across the element, right? And so this is kind of a good illustration to see, what it means to be a linear function. Right? Actually, I think I can zoom in. Let me go ahead and zoom in. That might be a little bit easier to see. Okay, there's like one too many bars here. All right, zoom in. Zoom. Let me do this. Okay, so here you can see it a bit more clear. So you can see that the solution kind of kinks right here, right? Right, and then after that, it becomes just a pure linear line, right? And so this should hopefully give you a bit more insight into what it means to choose an element order, right? And so when you choose a linear element order, that means in between nodes in an element, right? As you traverse from one end of the element to the other, that means your solution is going to be linear, right? And so it's hopefully you kind of see the relationship between what you're working on in the homework with the weak form, right? Because with the weak form solutions, as you see from the homework, the first thing that you do is you assume a form of the solution, and then remember you find the best form of that solution that answers that problem, right? And so here in finite elements, we're assuming the function is linear, we're assuming the solution is linear, and through the finite element method, what we do is we find the best linear function that will match this problem, okay? But it's still a linear function. So you're still making it linear. It's just that it's the best linear function that we can do. Okay, and that in essence is what the finite element method is for for these general problems. Is you assume a solution, you plug it in, and then you find the best function of that form that solves that solution across that single element. All right, and so are there any final questions on this? Okay, and so let me just go ahead and skip to the end of this presentation. And so, this is not going to be due anytime soon, and so we're not going to look. You're not going to do this until probably after the midterm exam. But what I want you to do is I want you to extend this code with the following changes. And so the changes I want you to make is that instead of a constant area, I want you to vary the area as a function of x. Okay. And then your thermal generation function is going to be a bit more complicated as well. So it's going to be x squared sine of pi x. Okay. And so the difference here is that for the s of x, actually that part's actually pretty easy to change. Okay. The difference here is that when you evaluate this expression, okay, this means when you're writing your code for the element stiffness matrix, okay, so when you write the code for KE, in order to evaluate this A right here, you're going to need to use Gauss quadrature. Okay? Because now you're actually integrating something. And so, for the activity that we've done so far, with a constant K and a constant area, you didn't have to actually integrate anything because, it all just ends up being constant. But now you actually have a function that you need to integrate. And the way that you do that in code is Gauss quadrature. Okay. And so this is good practice. And so it's good practice to do this in a 1D case because you're going to need to do it for for the project as well. Okay, so try it out here, and then you're going to apply that for the project as well. It takes a bit of practice to practice Gauss quadrature. So it's always good to practice it on a simple problem like this. Okay, and so that's the implementation. Okay, so let me go ahead and jump back to my iPad here, where we can start to talk about 2D finite elements. All right. And so this set of lecture notes, I call this the mathematical preliminaries. We're primarily going to be doing this for 2D finite elements, just because it's a lot more tenable to teach that in the class. But a lot of these topics are they extend to 3D as well. All right. So this is for 2D and 3D finite elements. Okay. So we've kind of already ran through the entire process for 1D finite elements, right? And so for 1D finite elements, we kind of had to dig up, a lot of mathematical tools and a lot of mathematical skills that, you may not have used in a while, okay? And so, just to sum it up kind of very, very simply, we can say that 1D finite elements use differentiation and integration to basically derive our, element stiffness matrix and element forcing vector. Okay. In particular, one thing that we had to do is we had to do an integration by parts, right? So I think that was kind of the most complicated step. And so for multidimensional finite elements, we're going to go through the same process, right? And so we're going to go through the same process in 1D, but because we are working with 2D equations, that means we're going to need to, use multivariable calc, right? And so the big difference here is that, when we're deriving our expressions here, we have to rely on, multidimensional calculus and vector algebra and vector calculus, okay? And so the point of this set of lecture notes, and it's only a half set, we're not going to be doing this for the whole week, is to kind of just perform a refresher from a lot of these topics. Because if your experience in college is anything like mine, then the math classes are very highly variable. And so I remember when I took finite elements for the first time, and the instructor started talking about, like, oh, you should have seen this before, you should have seen this before. My first reaction was, I've never seen this thing before in my life. And so, I want to make sure that we're all on the same page, that we all know what we're kind of talking about when I mention things like Laplacian and the gradient and Green's theorem. Okay, just so that we can all be on the same page, when we do this, in the coming lectures. Okay. All right. Another difference too is that because we're working in multiple dimensions here, we don't have a ordinary differential equation anymore. And so the governing equations that we're going to be looking at are partial differential equations. Okay. Okay. Right, and the main upshot with this is that with ODEs, we could solve those exactly. And so we could take the strong form of the equation and solve them in order to check our results. Right, that's a lot harder to do with PDEs. Okay. It's much harder to check results. Okay. And so that's going to be a challenge. And so, when we're going through, when we're developing the theory for the first time, when you guys are writing your code for the first time, it's going to be much more difficult to check your results. And so, that's always a challenge with multidimensional problems. Okay. All right. Any questions on this so far? Okay. All right, so let's start with some basic definitions. Okay. All right. And so let's start with kind of redefining what we mean by our domain. And so the notion of what we consider to be our computational domain or our problem domain is going to change depending on if we're in 2D or 3D. Okay. All right, so let's start with the 1D case. And so in 1D, our domain was a line, right? Okay. And so we just saw that in our code, right? And so when we solve a 1D equation, we're solving it just along a one-dimensional line. Okay. In 2D, when we add that second dimension, our concept of a domain extends to a surface. Okay. And then for 3D, in 3D, our concept of domain turns into a volume instead of a surface. Okay. It doesn't have to be a box, but with my limited artistic skills, that's the only three-dimensional object that I can draw that doesn't look like, that looks decent. Okay. Okay, and so that's important to keep in mind. And so, when we're doing 2D problems, our domain now is going to be this whatever two-dimensional surface that we can think of. Okay, and that gives us a lot of freedom, right? And so with 1D, there's only so many lines that you can draw, right? You can draw a line, and you can draw a slightly longer line, right? And so that's basically the only freedom that you have. But in 2D, you can make all different kinds of shapes possible, right? And so look at your project, right? And so for your project, you're doing a circular domain, right? Which is pretty cool. And you can have a square domain, you can have a J size domain, right? And so you can kind of do whatever you want. And in 3D, of course, you have a lot more flexibility. But of course, with that greater flexibility comes greater challenge as well. Right? Okay. And another difference that we're going to have is that our solution variables, they're going to become functions of multiple variables. Okay? And so in 1D, let's say that we're solving the heat equation. Our solution would just be t as a function of x. Right? Right? In 2D, right, we'd have two variables. Right? And so for instance, we can have t as a function of x and y. And of course, in 3D, you have x, y, and z. Okay. Okay. And one other important note, and this is the reason why we're not going to do elasticity, we're not going to do structures in 3D, is that in addition to your solution becoming a function of multiple variables, your solution itself will become multidimensional. Okay. And so for vector value solutions, and so one prime example of this is elasticity. Okay. Solution has multiple dimensions. All right. And so in 1D, like the ones that we solved before, a 1D, we solve for like a displacement, we solve for a deformation. It would just be u of x, right? One dimension. Right? So this is 1D. In 2D, you have ux and uy, okay? And both of these are going to be a function of x and y. And in 3D, you're going to have ux, uy, and uz, okay? And these are all going to be functions x, y, and z. And so basically, for vector valued functions, you basically have to solve the same problem multiple times. And so, you're going to be having a vector valued solution instead of a scalar one. Okay. And so, it's not, I wouldn't say it's not, it doesn't make the problem more complicated as you think. So it's not a big step up in complexity. I would say it's just kind of a step up in annoyance because you have to write everything twice. Okay. And so for this reason, for the reason that I don't want to be solving multiple things at once. Kind of from this point on in the class, we almost focus entirely on the heat equation. Okay. And the reason for that is that the solution to the heat equation is a scalar value. Okay. And so there's no temperature in each direction, right? Temperature is just temperature. And so, we can solve it just as a scalar function. All right, and so those are just some kind of basic definitions. And so, we have a concept of the domain. Our solution function is going to be a function of multiple variables, and our solution itself might become multidimensional too, depending on which equation that you're going to solve. Okay, any questions on this? Okay. All right, so let's talk about the boundary of our domain a little bit. Or in other words, what the concept of the boundary looks like. And so for 1D problems, when we talk about the boundary of a 1D problem, all we're talking about is just the endpoints, right? Okay. So here we have our line, and then we have the 2 points that kind of bound the line, right? And so we have two boundary points. So we have the left boundary and the right boundary, right? That's all we have because a line can only be bounded by points. Okay. Of course, once you step up in dimensions, the concept of the boundary was also going to change, right? And so I'm going to focus on 2D. Okay. And so for 2D, our concept of a boundary will instead be a line. Okay. All right. And so here's our 2D surface, right? And so around this surface, or the one that gives it shape, is a line that goes around it, right? And so what we can say is that the interior of the domain, I'm going to use the symbol gamma, okay? And then the boundary of that domain is going to be partial gamma. And so I think I used this notation kind of briefly before, but basically if you see just a partial in front of that, then we're talking about the boundary. Okay. And so this is going to be really important because, before I would say in the 1D case, our boundary conditions were fairly straightforward, right? And so we knew exactly where they are. Now that our boundary can be a lot more flexible and a lot more diverse, we have to kind of define it really carefully. Because now, we might have multiple regions in our domain that have, different kinds of boundary conditions. Okay. And you'll see once we start doing some problems. Another concept of the boundary that I want to go over that's going to be important mathematically is this concept of an outward unit norm. Okay. And so whenever you have a boundary like this, right, you can always draw a unit vector that points outward from the boundary. Okay. Right. And so one example is like this, but you could draw this outward unit vector on different parts of the domain. So you can have one like right here. Right, one right here. Just know that at every location on the boundary, you could create a normal vector that points outward. Okay, and so this n hat we call the outward facing or the outward unit vector. Okay, and this is going to be important for our mathematics because the direction of this is really important because whenever we're on the boundary, we always want to know, and we're always interested in knowing which direction points outward from that boundary. Okay. Because that's going to be important for us to know as we develop our equations, right? And so in our equations, you're going to see this n hat show up, right? So you're going to see this n hat show up as part of Green's theorem, Green's equation, right? And so just know that whenever you're on that boundary, that's where it points. Okay? We can actually kind of extend that same sentiment to the 1D case. Okay? For the 1D case, it's just kind of trivial. And so for the 1D case, we would have an outward unit vector that points this way, right? And an outward unit normal that would point that way, right? Because when you're on the left boundary, if you continue going left, that's going to lead you out of the domain. If you're on the right boundary and you keep going to the right, that's going to lead you out of the domain. Okay. Any questions on this? Okay. All right. So this next part, it's kind of implied, just because we're working with PDEs now, but we're going to have to get used to working with partial derivatives instead of normal derivatives. Okay. And so partial derivative, we instead of using a full derivative marker, we use a partial derivative. Okay. And so let's say that we're taking the partial derivative of f with respect to x, right? Where f here, let's just for simplicity, we'll say that f is a function of both x and y. Okay. And so mathematically, what this means, and if you go back to the old school definition of a derivative, right? And so this means as I always forget this. And so if we take the limit as delta x goes to 0, right? The partial derivative of f with respect to x is going to be f of x plus delta x comma y minus f of x comma y divided by delta x. Okay. And so in other words, this represents, okay, this represents the rate of change, or the rate that f is changing in that x direction. Okay. Right. So partial derivatives, I think, is something that ironically, or I should say unironically, is easier to understand mathematically, but more difficult to understand what it means in practice, right? And so I always like to think of this analogy when I'm thinking of partial derivatives, right? So do you guys know what a topology map is? And so if you've ever looked at a map that shows, different heights of different mountains in a certain region, it looks something like this, right? So you have a map, right? So let's say that this here is the top of the mountain, right? And so this here is the peak, okay? And then around it, you might have different contours, right, of differing heights, right? Right, so it's almost like you're looking at a mountain from kind of the top down. So you're in a helicopter, you're looking down, right? This is kind of what you would see. Where each of these lines right here, we call them lines of constant height. Okay. And so if the peak, let's say the peak is, I don't know, 100 meters off the ground, right? Then we'll say that this line is 90 meters. This might be 80 meters, 70 meters, 60, and so on, right? And so as you progress, to the different lines, right, then, you get closer and closer to the ground, right? So this is like a topology map. I think some people call it contour maps. They're all kind of, the same thing. In a situation like this, we can say that the height, right, that you're at is a function of x and y, right? Okay. Right, where of course the x direction is the horizontal one and the y direction is the vertical one here. Okay, vertical on the map, not vertical on the mountain. Okay. And so if we take the partial derivative, and so let's say that we take partial h, partial y. Okay. That means if you were physically, you're physically standing on the peak, right, and you start walking in the y direction, right, partial h, partial y is going to represent, how quickly your height is going to decrease, right, or how quickly you're going to fall and break all the bones in your body. Okay. Because when you have multidimensionality, and so when your solution or when your functions here depend on multiple variables, you can talk about how quickly it's changing in one direction versus the other one, right? And that's what the partial derivatives represent. Okay. All right, and so of course, you can have partial derivatives in all directions. You can have multiple partial derivatives. Okay. And so one you'll see right away, or see a lot, is something that looks like this. And so this is the double partial derivative. Okay. In this case, it's in the x direction. Right. And so it's the same concept as the double derivative. So this tells you how quickly the rate of change is changing. And so it's the rate of change of the rate of change. Okay. When you have multiple dimensions like this, you can also have what's called a mixed derivative. And so let's say that you take a derivative in one direction first. And so let's say that we take a derivative with respect to x, And then we take that function and we take its derivative as a function of y. Right? So this is called a mixed derivative. Okay. And while technically this is mathematically possible, physically it's pretty rare. And so, I don't want to say it never happens. My knowledge of applied physics and applied math is not nearly that exhaustive, but it's something that I personally almost never encounter. When you're talking about things like structural mechanics, when you're talking about things like fluid mechanics, heat transfer, mixed derivatives are almost never used. That doesn't mean that they don't exist, but for a lot of the applied physics engineering equations that I work with as a mechanical engineer, I don't really see them, but they are possible to exist. All right, any questions on this? Okay, and so that's just kind of basic definitions there. And so let's go over next vector calculus operations. Okay. And so these are going to be important because we're going to use these, and they're going to when you first look at them, they're going to look like just generic symbols, math symbols. But it's important to understand what they mean, intuitively. Right? And so the first one we're going to look at is called the gradient operator. Okay? And so the way this is usually denoted is we take this upside down triangle. Okay? And so that upside down triangle, if you're ever wondering what that means, the name for this is called a nabla. Okay? And so to compute the gradient of a function, we take nabla times f. Okay. Okay, and so the definition of the gradient kind of builds directly off our definition for partial derivative, right? And so we know that if we have a multivariable function, we can compute its rate of change in each of the different directions, right? And so the gradient, you can think of it as kind of, computing those derivatives in every single direction. Okay. And so, let's say that we have f is a function of x and y, right? And so when we compute the gradient of f, that means we're going to compute the rate of change in x, the x direction, and the y direction. All right, and so gradient of f, it's important to note that this is a vector quantity. Okay? Right, and so the first component of the vector is going to be the partial derivative of f in the x direction. And the second component is going to be the partial derivative of f in the y direction. Okay. And this is an important property I want you to remember for gradients as well. And so what they do is that they increase the dimensionality of your function by 1. Okay. And so if you take a gradient of a scalar function, you're going to get a vector. And if you take the gradient of a vector function, you're going to get a tensor, or you're going to get a matrix. Okay. And so as an example, if you needed further motivation of why we don't do, why we're not doing 2D elasticity, right? Here's what it would look like if we took the gradient of the deformation function. Okay? Or excuse me, this is in 3D, right? And so if we take the gradient of the deformation vector, okay, it would be a 3x3 tensor. And so we have partial ux, partial x, partial ux, partial y, partial ux, partial z. Okay. Then we have partial uy, partial x, partial uy, partial y, partial uy, partial z. Okay. We have partial uz, partial x, partial uz, partial y, partial uz, partial z. Okay. And so you end up with this kind of 3x3, tensor monstrosity, right? And so imagine kind of working with that, through a complicated PDE, with integration by parts and everything. And so, it's possible. Obviously people have solved this. If you do CFD for fluid mechanics, you have to deal with this as well. But for this class, where we're just kind of learning how to do finite elements for basically the first time, it's just kind of a little bit too much. And I think it's one of those things where you kind of get lost in the details and you kind of miss the forest for the trees, basically. Okay. All right, any questions on gradients? Okay. All right, so that's the first operation that that I want you to know. The second operation is called the divergence. Okay. And so the divergence is it's not exactly the opposite of the gradient, but it has a lot of properties that are opposite to it. Okay. And so the way that we get the divergence is we take the nabla, okay, and we take the dot product of that between that and our function. Okay. And so we have nabla dot u, okay, where u is a vector valued function. Okay. And so if we do that, then we get the partial derivative of the x component of u with respect to its own component. And so we have partial ux, partial x. And to that, we're going to add partial uy, partial y. Okay. And then we have partial uz, partial z. Okay. And you simply just kind of add them all up together. Just like that. Okay. And so physically, the reason it's called divergence, and so because it kind of shows how much your solution is diverging from a single point. And so I think the best analogy I can think of this is in terms of fluid mechanics. And so if you have a droplet of fluid, right, what the divergence kind of represents is how much that fluid is kind of spreading out in all those directions. And it kind of gives you a single number that represents that. Okay. But the most important thing I want you to remember for divergence is that it reduces the dimensionality of your function by 1. Okay. And so if you take the divergence of a vector, then you're going to get a scalar. Right? If you take the divergence of a tensor, you're going to get a vector. Right? And so it does the opposite of a gradient. So gradient increases your dimensionality, divergence reduces it. Okay. Any questions on divergence? Okay. All right, and the last one that I want to go over is something called the Laplacian. And so the Laplacian is basically a combination of the two operations above. Okay. And so the way that you get the Laplacian is you take the divergence of the gradient of a function. Okay. Okay. And that function can either be scalar valued or vector valued, but just for simplicity, we'll assume that the function is scalar valued. Okay. And so mathematically it looks like this. We take the divergence, but instead of just a generic vector valued function, another way that we can generate a vector valued function is to take a gradient of a scalar function, right? And so f by itself is scalar valued. Okay. But the gradient of f, this is vector valued. Okay. Right? Because remember, you take the gradient of something, it increases its dimensionality by 1. Okay. Then you're going to take that and you're going to take the divergence. Okay. And of course, the divergence reduces the dimensionality to 1. And so we go from a scalar to a vector, then back to a scalar. Okay. And so the shorthand notation for the Laplacian, you might see it as, nabla squared f. Okay. And then mathematically it looks like the following. And so you have partial squared f, partial x squared, plus partial squared f, partial y squared, plus partial squared f, partial z squared. And of course, this is its expression in 3D, but in 2D, you would just knock off the z component. All right, so the reason I bring up the Laplacian is that the Laplacian is very common, and so you see it a lot in heat equation type problems and in structural mechanics types of problems, and so it shows up in those kinds of equations quite a bit. All right, any questions on this? Okay, so now that we have a lot of the basic definitions out of the way, so maybe you've seen this before in previous classes, maybe not. Okay. But now we kind of move on to the more important part, which is how do we take these concepts and apply it to finite elements, right? And in particular, what we want to be able to do is we want to take a multidimensional problem, like multidimensional heat, multidimensional elasticity, and we want to derive its element stiffness matrices. Okay. And so a big part of that, if you remember from our finite element formulations before spring break, a big part of that is being able to take a multidimensional function and perform integration by parts. Okay, and so the next thing we're going to learn is how to do integration by parts in multiple dimensions. And there's a specific theorem for this, and it's attributed by some dude named Green. Okay, and so we'll go over Green's theorem and Green's formula. Okay. And so the goal of this is to perform integration by parts in multiple dimensions. Okay. All right. But before we do that, let me go ahead and remind you what the 1D integration by parts looks like. Okay. In particular, let's look and see what it looks like for 1D elasticity, right? And so I'm going to use the symbols for 1D elasticity. But remember, for 1D elasticity and heat equation, they have the same equation, right? And so the equation for that is we have an integral, right? We have an integral from 0 to L. And we have w of x, which is our weighting function, times d dx of e times a du dx. Okay, dx. This is equal to w of x ea du dx. Okay. Evaluated at x is equal to gamma gamma omega n, okay, minus integral from 0 to L dw dx EA du dx dx. And so this was our integration of by parts in 1D. Okay. Okay. And so before we jump into how we do this in 2D, I want to examine this and I want to kind of label what these terms represent. Okay. And so let's start with this first one right here, right? And so you can see by performing integration by parts, we break up our original integral into two separate terms. Okay. And so the first term that we have here is a is a term that's not an integral, right? And so that's the first thing you notice about this first term. It's not an integral. Okay. And so what we're doing here is we're evaluating the integrand, okay, or part of the integrand. Okay? And so we're evaluating this at the locations of the Neumann boundary. Okay? Okay. And so it's not something that gets evaluated throughout your domain. And so it only gets evaluated at the just wherever location has the Neumann boundary. Okay. Our other term here is an integral, right? So this is still an integral. And it has the same integration bounds as the original integral, right? So from 0 to L. And so this is the same, it's an integral over the same domain, okay? But mathematically, it has a different structure, right? And most importantly, from the structure, you can see that our two functions here, W and U, they have the same order of derivative. So what we say is that these derivatives are balanced. Right, and so the result of our integration by parts is that we get these two expressions. So we have one expression that's evaluated on the boundary, specifically the Neumann boundary, and then we get a kind of like a repeat, almost like a repeat of our original integral, but with balanced derivatives. Okay, and so that's going to be our goal with the multi-dimensional integration by parts, is that we should get both of these terms, both of these types of terms, mathematically in our result. Okay, and so let's keep that in mind as we go through our derivation here. Okay. Okay. And so our first step here is the statement of Green's theorem, right? And so we're just going to state this one outright. And so the original Green's theorem, it's stated in 3 dimensions. And so I'm going to do a lot of this derivation in 3D, but I'll show you the 2D version of it later. But first, I'm just going to focus on 3D. Okay. Okay, and so what Green's theorem states is that for a scalar function, okay, and so the scalar function is going to be f of x, y, and z. Okay. And so what Green's theorem says is that the volume integral, or the triple integral, of its gradient is equal to or equivalent to the surface integral of f on that same domain. it's kind of a mess of words, but I think it's easier to kind of express mathematically. Okay. And so the first part of this is that we have a triple integral of the gradient of f, right? So we'll start with the gradient of f. Okay. And let's take the triple integral. So we have three integrals here. And since we're doing three integrals, then our integration variable here is going to be dv, where the v here stands for volume. Okay. Okay. And so this is equivalent to a surface integral. Okay. And so a surface integral here is a 2D integral. Okay. And to denote it from a regular 2D from a regular double integral, I'm going to put this kind of circular pattern on it. Okay. And then we're going to take f, and then we're going to dot product with n. Okay. N hat, remember, is our outward unit normal, and that's going to be on the boundary of v. Okay. All right, so notice the subscripts that I put on these integrals here. So on one side I have v, so v representing kind of a volumetric domain, and then I use partial v to denote its boundary. Okay. So that's really important. And so these can't just be two random integrals on two random domains, right? And so let's say our domain here is this kind of box. Okay. Right. And so let's say that this box is our domain. And so when we take the triple integral over this box, that means we're integrating over the volume of that box. Okay. Okay. And so you integrate over the volume of the box, that's our triple integral. Okay. This surface integral right here uses the same box, but instead of integrating through the volume of the box, we're only integrating on the surface of the box. Okay. Okay. Right. So that's really important. And so that's really important that we make that distinction. Okay. And so that's Green's theorem kind of just stated straight up. And so basically you can take a region integral, right? Or an integral that pierces through an entire domain, and we can say that we can form an equivalent integral that just goes around the boundary of that domain. Okay. Okay, so this is just one ingredient for us to do an integration by parts, right? Because remember, if we look back at our integration by parts in 1D, a big part of that is to take, this which we consider to be a integral over the domain. Okay, this is our integral over 1D domain, and then part of the integration by part is to extract out a component that is just evaluated on the boundary. Okay, and so believe it or not, this Green's theorem allows us to do just that, right? Except the concept of what's our domain and what's our boundary is different in multiple dimensions. Okay, and so as opposed to 1D where our boundary is just discrete points, in 2D and 3D, our boundaries are now full-on lines or full-on surfaces. Okay, so that's kind of the big difference here. Okay, any questions on this? Okay, and so let's take Green's theorem, and since we know, right, we know that the gradient of a function is a vector, right? Right. Let's take Green's theorem and write it out in its different components. Okay. Okay, and we're going to have 3 because we're in 3D, right? And so we have the x component. And so the x component of this is going to be triple integral. Okay. The x component of the gradient of f is going to be partial f, partial x. Okay. dv is equal to surface integral of f dot product with the x component of the normal vector. Okay. So remember, the outward unit normal is a vector, and so it's going to have components in the x, y, and z directions. Okay. Next, we have the y component, and so it's going to be the same thing. So we have triple integral, except this time we're going to have partial f, partial y, dv. Okay. And this is equal to the surface integral f dot ny dA. Okay. And then finally, we have the z component. So the z component, we have triple integral, partial f, partial z, dv is equal to double integral f dot nz dA. Okay. Okay, so this is, and so that's what each of the components of the Green's theorem looks like. Okay. And so up to this point, what we say is that f is just some generic function. And so, the next step in Green's formula is to plug in a specific value of f or something more specific in f. Okay. And in particular, because ultimately we're going to use this for weak forms of finite elements, let's plug something in for f that relates to our weak forms. Okay. And so let's say that f is equal to, let's say that f for each of these, okay, is equal to w, the weighting function, multiplied by partial t partial x. Okay. And so we're going to make this substitution in for each of these, but we're going to do it according to the dimension. And so for the first one, right, this is what we're going to plug into the first one because that's the x component. But we're also going to plug in f is equal to w partial t partial y for the second one. Okay. And for the third one, we're going to do f is equal to w partial t partial z. Okay. So that's what's going to go into this one right here. Okay. Okay. Well, before we do that, we can see here that we're taking partial derivatives of this, and so we're going to need to do some chaining. Okay. Okay. And so if we have partial f, partial x, right, and if this is our new value of f, right, then we're going to take partial x of w, partial t partial x. Okay. Where both w and t here are functions of x, and so if we chain rule this, we get partial w partial x, partial t partial x, plus w partial squared t partial x squared. Okay. Okay. And so if we make the substitution, and so if we basically plug this in, right, we plug this into our Green's theorem. We plug into Green's theorem and we get the following expression, right? And so we have, for the x component, we have triple integral partial w, partial x, partial t, partial x, plus w, partial squared t, partial x squared. Okay. And this is integrated with respect to volume. Okay. This is equal to surface integral of w partial t, partial x, dot product with nx dA. Okay. Right. And so all I've done is just plug into our Green's theorem. And so now we have a more specialized version of f. Okay. And since the f here is comprised of two different functions, we had to do the chain rule. And so that's why we have kind of more terms than we did before. Okay. And so I'm gonna take this process and repeat it for the y and z directions. And so for the y, we have triple integral v partial w, partial y, partial t, partial y, plus w, partial squared t, partial y squared, dv is equal to surface integral w, partial t, partial y, dot ny dA. Okay. And then for z, we have triple integral over the volume, partial w, partial z, partial t, partial z, plus w, partial squared t, partial z squared, dv is equal to surface integral w, partial t, partial z, dot nz dA. It's a lot. I know it's probably more partial derivatives and more integrals that you probably ever want to see in your life. I know it's a lot, but I promise you the result is a lot simpler than this. And so, the way this derivation kind of works is that we kind of break it up into components first, and it makes it seem like this just ungodly mess. But later on, once we kind of combine everything together and put it back into vector notation with gradients and divergences, it's going to simplify quite a bit. Okay. And in the end, we're going to get an expression that looks very similar to our 1D integration by parts. It's just that now we're kind of replacing all those 1D operations, all the 1D integrals and 1D derivatives with like things like gradients, double integrals, triple integrals. And that's what we're going to end up using for our 2D and 3D finite elements. Okay. And so, I kind of hate to leave it right here, but, we are just about out of time. And so, there are, 2 or 3 more steps to this derivation. But, I don't want to keep you guys, past the time. And so the next step, just so you have a sneak preview. And the reason I didn't want to proceed is that we're going to take all 3 of these and we're going to add them together, right? And so we're going to have just a massive triple integral on one side, a massive surface integral on the other side. Then it's just kind of plain matchmaker. And so we're going to be rearranging the terms, matching them together, right? And that's going to give us our expression in the end. Okay. But we'll do that next time, just because it's a little bit tough. All right. Any final questions on this before we wrap it up for today? Okay. All right. So that's it for today. And so on Wednesday, remember Wednesday is going to be purely virtual, and so I'll be streaming from my apartment. And we'll pick up here where we left off. All right, so thank you everyone for tuning in today. Hope you guys enjoy the rest of your evening, and I will see you virtually on Wednesday. Yep.
You mind if I step outside for a minute or two, or you help me out?
Okay.
I can't get going after that.
Okay. Yeah.
I'm trying to decompress.
Okay. Yep.
And then I think Kamal has questions too, but his USB is in a metal case. And he looked at it during class and the inside is missing.
Oh.
Yeah, so he lost all his project files for our CATIA class and everything.
Oh,
so he's looking for that right now.
Oh man. Well, I hope he finds it.
Hopefully just keep on.
Timothy, Camille, are there any questions before we wrap it up? Okay.
Yeah, I was actually having some issues with 3C on the homework.
Okay. All right, let me, you want to share your screen so you can, so I can see?
Oh, I work on
Or did you have
paper.
was it kind of a text question or? Let me
I'm
pull
just
it up here.
confused on the Neumann boundary condition, because in the notes, it, sorry, wait. I think if I share my screen, it would help better.
Okay,
It says host disabled participant screen sharing.
let me go ahead and change that. All right, go ahead.
So, whoops, and of course I'm not on the correct section, sorry. This part,
Okay.
because it says W0, but
Yeah,
isn't W0 supposed to be 0?
right. So for that first derivation, we did it for kind of a specific case where the Neumann boundary condition was at x is equal to 0. But for this one, 3C, the Neumann boundary condition is on the other side. So it's when y is equal to L, right?
Right.
And so you're going to need to replace that expression with W of L and A of L instead.
Okay.
Yeah, and so the one we did, and so it's a little bit. I mean, it's my fault for the way I structured these notes. So the first time we did a weak form like this, I did it for a specific case where the Neumann boundary condition is at 0, but the more general case is actually in the heat in the thermal heat transfer one, where I kind of make it more general to be evaluated just wherever the Neumann boundary condition is. And so that's the one you need to apply for this problem is, just wherever the Neumann boundary is, wherever the natural boundary condition is, that's where you apply that term.
Okie dokie. We'll do that. Thank you.
Yep.